Hello folks, this is Dr. Young, and this is the second part of our quantum numbers and orbitals discussion. In this part, we're going to talk about the quantum number L, which is the angular momentum quantum number. It's a really important one because it tells us what type of orbital are we looking at, S's, P's, D's, or F's. So remember we went through this big old journey, we watched all these previous videos. I'll just cut to the chase. We are now here. We're talking about the second of the four quantum numbers, and remember that the four quantum numbers are the numbers that sort of describe what these orbitals look like, what these probability maps for where an electron is, what they look like. Right? We talked about this before. Schrodinger created this mathematical equation. We have these wave functions, which is where electrons are probably, given that they have this wave-like property. If you square that, you get the probability of finding an electron, and that these are called orbitals. Even though there's really nothing orbiting, we still call them orbital. In the previous video, we said that this n number, right, this principal number, that referred to sort of the shell or the main, it's called the principal number, it's the main energy, the main size of it. So that would correspond directly to the 1 here, or the 2 here, or the 2 here. Well, that's the number that's going to be in front there. And we just look at the periodic table, see what period you're in, and that's usually your quantum number. If you're in the D block, it's -1 from your row number. If you're in the F block, it's -2 from your row number. What we're going to talk about in this video is the L, which tells you what type of orbital, what's the shape of your orbital. So like in this example, S, the L is going to be described by an S here, same thing for the S here, and then it's going to be a different L number for the P here. So I'll just say this now, L is 0 for S, L is 0 for S, and L is 1 for P's. That's kind of the code that we're deciphering. So let's take a closer look at L and ask ourselves some questions about it. So again, here's my big table, right, of the four quantum numbers. We already did the principal quantum number, check, right? We said it can have values from 1, 2, 3, 4, in theory up to infinity. Realistically, on a periodic table, we're not going above like 7 or so. Now we're going to talk about the angular momentum number, right? So this is the one we're talking about now, which tells you the shape of the orbital. So it tells me, how do I know if I'm talking about an S orbital, a P orbital, D orbital, F orbital, G, in theory, G, H, I, J, K. It could just go on forever. For angular momentum, and I'll say this again in a second, the allowable values, remember that this is a mathematical concept, the allowable value, it turns out, is that your L can equal 0, and then all the integers up to your n minus 1. So if your n equals 1, 0 is your only allowable value. If your n equals 3, then you can go up to n minus 1, or in other words, 2. So if your n is 3, then the allowable values are 0, 1, and 2. And I'll talk more about this in a second. But it tells us the shape. And this is a really, really important one because this is going to help inform how atoms bond. So helps to understand how atoms bond. And we're not going to do any bonding right now, but in the future we will, and we'll talk about like, oh yeah, the two S orbitals overlap and they create a new, sigma star orbital or something like that. But if you don't understand what an S orbital is, then that's not very helpful. Or if we say, oh, pi bonds are always between two P orbitals, that is not going to make any sense if you don't understand what a P orbital looks like. So that's what we're talking about right now. So like I said, right, the principal quantum number, oh, sorry, this is not the principal quantum number. This is the angular momentum. Excuse me. So the angular momentum quantum number is L. Is this L, this little scripty L guy. And like I said before, the allowable values are from 0 all the way up to n minus 1. So whatever your n is, and I'll show you this on the periodic table in a second, but whatever your n is, you subtract 1 from it, and you can go up to that number in full integers. And what the code is, right, this is really good to know. Here's the secret code. Always, 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 if your L is 0, that means we're talking about an S orbital. So that means that all of these suckers right here, right, this is the shape of your probability of finding an electron when your L equals 0. It's always going to be an S orbital. So it's going to be this spherical S orbital. Whenever your L equals 1, that's talking about P orbitals, which are these sort of dumbbell-shaped looking things, right? There's two lobes on either side of where the nucleus is. And I should mention this now if I haven't said this before. The nucleus is supposed to be at the very center of these things. Right? This is your nucleus in the center, and then the electrons are around are located around the nucleus. And so this describes, well, hey, if your electron has a certain energy, it's likely to be found in this sort of shape. And I know these shapes look kind of funny, but I want you to think back to, right, the plucking of a string and how there were only certain allowable values, stable values for a wave to have, right, a certain allowable energies, or in other words, certain quanta, certain quantum energies that things were allowed to have. If you go up to, if you go up to the d orbitals, that's when your L equals 2, and here you have d orbitals. We'll talk later about why there's so many d's and so many f's, for example. Right now, I just want you to know that when you have these different L values, you're talking about a different type of orbital. So when L equals 3, here's your L equals 3, then you're talking about the f orbitals, right? Which is, again, kind of what I set up here, right? So S, P, D, F. Now, again, in theory, there's G. I mean, you could keep on going. You could expand this list. When your L equals 5, you'd go to H orbitals. When your L equals 6, you'd go, what is that, I? And you could just keep on going through the alphabet. Now, realistically, the ones that you're only going to see from the periodic table are up through 3, are up through 3. I don't know of anything that has a G orbital. Those elements are not in existence. But in theory, you could keep on going. And this math, since it's a mathematical concept, could keep on going. Realistically, for us, we're going to see S orbitals, P orbitals, D orbitals, and F orbitals. And here's the rough shapes of them. Now, so let's take a look at this again. Remember that I said that your helium really belongs over here. So I'm going to move our helium friend back over here, not there. And recall, right, that we had the S block, right? We said this was the S block. We said that this was the D block. This is the P block. And then lastly, we have the F block, which inserts itself right here. Now, what we can say now is we can say, oh, okay, well, let's pretend we have a well, let's just look at this, right? So we can further refine this now. Now we can say that these are the 1s's, these are the 2s's, because remember that this is 1, 2, 3, 4, 5, 6, 7. And you could just go down. You could be like, oh, well, these are the 6s's, these are the 7s's. But you could go so far as to say, like, well, what about this? What about this whole row in the D block? Now remember that the n for this, the principal quantum number, is the row number -1. So these are the 3 Ds. Just like these would be the 5 Ds, because, right, I took row 6 and I subtracted 1 to get 5. So I know these are the 5 D orbitals. And you could do this for the P's, right? Here's a row of P orbitals. That's in the 3rd row. So those are the 3 P's. Or maybe right here would be the 4 P's. And then like this for the F's, right? Remember that the F's were the row number -2. So this really belongs here with the 6, right? This is where the cut-in is at 6. So these would be like 4F values. And these would have really different shapes, right? Something like a 1s would be spherical and round. A 2s would also be spherical and round, but bigger, right? Whereas a 6s would be even bigger. But a 3D is going to look something totally different. It's going to have sort of this like clover shape, and that's going to be aligned in different ways. A 3P is going to have this figure 8 sort of look. And you'll notice here, I don't know if I should talk about this now or later, but you'll notice here, and I'll show you these orbitals again later, but they have shaded and unshaded parts. The D's and P's have shaded and unshaded parts, or lobes that are different colors. Notice I left this one white and I colored this one blue. That's going to be important later for when you try to bond stuff. And so we'll come back to that. But the lobes have different colors. Whether or not you see that in a book, them having different colors, they have different colors or different phases. And I'll talk more about that in the future. Right now, what we're focusing on is the fact that I can look at these, and if it's an s orbital, right, what I can say is, oh, all these s orbitals, I know that all of these s orbitals, all of these s orbitals have the same angular momentum value, which namely is 0. right? All of the d ones have an angular momentum value of 2. All of the p orbitals have an angular momentum value of 1, because that's what defines them, right? If your L value is 1, you're talking about a p orbital shape. You have that sort of dumbbell shape. If you're talking about your angular momentum value being 0, you're talking about a spherical shape for your probability of where to find the electron, and that would be the s orbitals. So that's what we're talking about with with the L number. And then here's a periodic table I just got from Wikipedia, which is showing you kind of what I showed you on the previous slide, right? Here is your S block, the 1s, 2s, 3s, 4s. Your D block, notice that it goes from 4s to 3D to indicate that -1 that I was talking about. But then it goes back to 4p because the p's you don't subtract anything like that. And they showed helium being over here on the right, but remember that helium is part of the S block, so they colored it the same color, that pink color, but helium would be over here. And then your F block, your 4Fs and your 5Fs. And so what we're going to start doing is we're going to start looking at specific elements and be like, oh, if you're the element that is in this block right here, the idea, and let me just highlight that a little bit here, right? If we're talking about this element, which is copper, what we're saying is that copper has all of the orbitals leading up to it. So we're going to read the periodic table like a book, top to bottom, left to right. So this copper apparently has 1 S's, and then it has 2 S's, and it has 2 P's, and then it has 3 S's, and then 3 P's, and then it has 4 S's, and then 3 D's up to here. But it doesn't really use like a 5p or a 5d or a 4f because copper isn't that low on the periodic table. And so we're going to start predicting what types of orbitals the elements have and where do they have electrons, which orbitals are being filled by electrons. So I could say, like, what orbitals does boron have, for example, right? So if I look at the periodic table, boron's right here. So I'm saying, what orbitals does boron have? Again, since I'm reading this like a book, I'm going to start here, and I'm just going to read across like this, right? So I know I just went through the S block, so this would be 1s, right? This is the S block. My D's, my P's. So I went through the 1s's, right, because I know this is number 1, number 2, number 3, 4, 5, etc. So I went through 1s, that's this row. But if I keep going, I've run out of elements, so I go down to the next row. So this is first, this is the second, so now I go through the 2s's. Sorry, 1 second. So I go through the 2s's. So now it has 1s's and it has 2s's. And then if I keep on going here, right, I go through and I hit the p's. The boron is in the p group, but this is the 2 p's. So now I know boron also has 2 p's. So boron, apparently with its 5 electrons, those electrons are in 1s orbitals, 2s orbitals, and 2p orbitals. And I can arrange those by energy in the order in which I read them. So I know that 1s's have the lowest energy, 2s's have the second lowest energy, and the 2p's have the highest energy because that's the order in which they showed up, right? This is the first read, first on the periodic table. This is the last on the periodic table. And we'll talk more about how many subshells are in the p orbitals. But right now, I just want you to kind of connect how to read the periodic table to what types of orbitals these elements have. So if I said what orbitals does boron have, I would say that it has 1s's, 2s's, and 2p's. That's where it has its electrons. But what if I picked a bigger element, right? What if I picked silver, right? So silver is right here. It's in the D block. And as you can imagine, this is going to be a lot bigger, right? So again, if I start here, that's going to be right away my 1s's. And then I'm going to keep on going. That's my 2s's. I'll keep on reading all the way through my 2p's. And then I loop around. I go further down. Now this is my 3s. And I'm going to keep on going. Now I went through, go through all the way through my 3p's. And now I have to go through my 4s's. And now I'm in the D block. These are the 3 Ds, right? Because it's the D block, but I'm in the third part, right? These are the 3 Ds. And maybe I should write this, right? This is the 1s, 2s, 3s, 4s, 2p's, 3p's. If I keep on going here, now I'm going through the 4p's. Keep on going on. I'm almost to copper. I'm almost to silver, excuse me. I'm in the 5s's. That's where the 5s's are. And if I keep on going, it looks like silver is located in the 4D block. And again, this is the orbital. This is the order in which you go from lowest energy value to the highest energy value. And so if I wanted to make an energy diagram of these orbitals, I would fill them in that order, right? I'd have the 1s's down here, and then the 2s's, and then the 2p's, and then the 3s's, and then the 3p's, and you just keep on going, right? 4s, exactly the order that we read them from the periodic table. And I'm kind of prepping you. What we're going to do is eventually you're going to have to do electron configurations where people say where the electrons are. And they say, oh, it's a 1s2, 2s2, 2p3 type of atom, right? That describes how many electrons it has. We're going to work our way to there, but I want you to start, again, connecting, reading the periodic table in order and connecting it to their energy values, right? 1s's are the lowest energy in this case, 4d's are the highest energy in this case. You can also be asked other questions, kind of like this here, right? So what orbital has an n equals 5 and an L equals 0? Well, I know L equals 0 is talking about s orbital, so this must be a 5s orbital, right? Because the principal number is 5, so you put a 5 in front, and it's an s, which corresponds to when your L equals 0. If I do go to this one, my L equals 2, which was the D's, right? S. Remember that when L equals 0, that's S. When L equals 1, that's P. When L equals 2, that's D. And when L equals 3, that's F. So this is a 2, so these are D orbitals. And there's a 3, so apparently this is a 3D. And you also want to check while you're doing this that you're following the acceptable rules, right? Remember that your L has values of 0 up to n minus 1. So for this one, your L numbers could have been 0, 1, 2, 3, and 4, right? Because 4 is n minus 1 since your n is 5. For this one, your L's could have been 0, 1, and 2 since n minus 1 is 2, right? Because our n is 3. Now, occasionally you might be asked a question like this, which is sort of like a trick you, I got you question. This one cannot happen. This is not allowed, right? Because your L values for this one, if n equals 2, you can go 0 or 1, right? Because 1 is n minus 1, which means you cannot have an L equal to 2. It's not allowed by these quantum numbers. Or another way to say this is that there is no such thing. There is no 2D orbital. It's not allowed by these quantum numbers, which again describes the probability of finding an electron in a certain area. There's nothing that looks like that. So just kind of check, right? You still want to make sure that you follow these rules for what are acceptable values for the quantum numbers. And then you might also see questions like this one right here, which is just saying how many types of orbitals, right, how many L values, are allowed when n equals 4. So that's kind of what we were doing before, right? Where n can equal 0, 1, 2, or 3. Again, I stopped at 3 because that's n minus 1, right? That's 4 minus 1. So my answer for this would be there would be 4 types of orbitals. Right? I can have when L equals 0 or 1 or 2 or 3, hence 4. So I hope that gives you a little bit better idea of what the L is referring to. It's referring to what the shape of that orbital is. So we've talked about this, right? We've talked about the N, we've talked about the L. Next is going to be the M sub L, which is going to kind of inform us why there are like 3 p orbitals and why there are 5 d orbitals and 7 f orbitals. That's going to be in the next video. So review this if you have any more questions, and please watch the next video. We're going to hopefully expand our understanding the more we talk about this. So watch the next video. Good luck.